type of problem you'll be given is where you're given the region. And so to find the area, we're going to notice that, all right, my graphs intersect at 1, 1 over here on the left. They don't intersect on the right, but it's obviously the graph is shown to be cut off here at x equals 4. And my graph above at the top is 1 over x. My graph at the bottom is 1 over x squared. And notice that 1 over x lies completely above 1 over x squared on the interval 1 to 4. And there is a representative rectangle that I'm summing, where the top of it comes from 1 over x and the bottom of it comes from 1 over x squared. So since 1 over x is greater than 1 over x squared everywhere on this interval, I can just find the area of this shaded region by the definite integral from 1 to 4 of the difference between those two functions. So another type of problem you'll see is where you're supposed to sketch and find the area, and you're just given the equations. You're not given a picture. So for example, we're supposed to sketch the region given by y equals x, y equals sine x on this interval. So you want to always sketch it yourself, but we can think about, okay, which is going to be the graph that lies above the other. And if you think about this interval, pi over 2 is approximately 1.5, and pi is approximately 3. And you know that the range of sine x is -1 to 1. And you know that on pi over 2 to pi, y equals x starts at pi over 2 and ends at pi. So y equals x is going to give me values above y equals sine x on this interval. So we can anticipate when we do sketch it that y equals x is going to be above y equals sine x. So when I set up my integral, it's going to be that the limits of integration will be from pi over 2 to pi, and my upper graph is x, my lower graph is sine x, so this is my integrand, x minus sine x, and I just find the definite integral of that difference. Now sometimes one function is not always above the other function on the interval, so sometimes they're going to intersect and cross and reverse. So here's an example: f of x equals cosine x and g of x equals minus cosine x. So notice that the interval we're interested in is 0 to 2, and f of x is above g of x on 0 to pi over 2, but g of x is above f of x on pi over 2 to 2. So in a case like this, we need to find where they intersect and break it up into two regions. This cosine x intersects minus cosine x on this interval at pi over 2. So we're going to set up the integral where we're subtracting g from f on the interval from 0 to pi over 2, yet we're subtracting f from g on the interval from pi over 2 to 2. So when you have a region like this, you need to break it up into two definite integrals. And here are the integrals. So 0 to pi over 2 of cosine x minus cosine x gives me this area. And the integral from pi over 2 to 2 of minus cosine x gives me the area of this region. Here's an example where the graphs are, instead of being functions of x, are given as functions of y. So in this case, we're going to want to integrate with respect to y instead of x. So instead of using a vertical rectangle, what if we just left stuff in terms of y and integrated with respect to y? So what we're doing there is using a horizontal rectangle. And now in this case, I wouldn't have to have two regions because this red graph is always to the right of this green graph, which means that the x values that this red graph, which is f of y equals cosine y, the x values that this outputs are always larger than the x values that g outputs. So I have a lot simpler of an integral now if I integrate with respect to y. So my y values go from 1 to pi over 2. Those are my limits of integration because I'm integrating with respect to the y-axis now. And my larger function values come from f because that's always to the right. And my smaller function values come from g because that's always to the left on this interval. So this is the area is given by this definite integral from 1 to pi over 2 of f of y, which is cosine y, minus g of y, which is minus cosine y. And there is my area. And notice I have dy here, not dx. And that comes from the width of this little rectangle that's horizontal now and summed with respect to the y-axis, not the x-axis. So now if I expand this region so that it's above that intersection point between f and g, I would again need two regions, just like I've seen before. I would need to integrate with respect to y again, but this time I would go from 1 to pi over 2 of with the integram being f minus g, because f is always to the right of g. And then for this region, I would integrate with respect to pi over 2 to 2. But in this case, g of y is to the right of f of y. So my integrand, I'm subtracting in the reverse order. And again, I do what I did before. I find each individual definite integral and sum them.